Hello, my name is Daniel Crestina. I'm a professor at the Politecnico di Milano, where we grow silicon germanium heterostructures, in this case for quantum dot qubit applications relevant to the IGNITE project. Semiconductors are natural materials to use for spin qubits. Especially silicon is the dominant semiconductor and the dominant material in technology. So if we could make qubits from silicon, the path to integration with existing technology would be very easy. The use of electrons in silicon, however, while it has the advantage that there's no nuclear spin in silicon, so the lifetime for spins of electrons in silicon is very long, unfortunately, it's not a natural material in which to perform these kinds of operations. The energy splitting between spin states is actually relatively low, so a strong magnetic field needs to be applied in order to create some splitting in energy between the spin states. The spin-orbit coupling is relatively weak. The spin-orbit coupling would allow us to flip the spin states not using a magnetic field but using an electric field. In order to create spin-orbit effects which are strong enough, however, usually in electron-based qubits in silicon, some magnets are actually placed within the structures in order to create these spatially varying magnetic fields. And that's inconvenient, and even that means that magnetic field doesn't speed up the operations. The operations remain relatively slow when we apply the time-varying electric field. The effective mass in silicon is also rather large. This means that the qubits, in order to define single quantum dots, need to be made very small, and this is challenging for integration. By small, I mean tens of nanometers. Gallium arsenide as a semiconductor is also very well known. It's maybe not so dominant as silicon, but it's known in optoelectronic applications and also for some very high-speed electronic applications. So it has its own path to integration. In this case, the spin-orbit coupling is stronger, so the operations can be faster, and the effective mass is smaller, so qubits can be larger. However, both gallium and arsenic have nuclear spin, and this means that the hyperfine splitting causes the lifetime of spins of electrons to be very short because there is this random varying magnetic field effectively in the material. And in this case also, the energy splitting between the spin states is relatively weak for electrons in gallium arsenide, which again requires strong magnetic fields. Germanium is a natural choice, not just because our growth system is using germanium, but because holes in germanium solve most of these problems at the same time. Germanium as a material is compatible with silicon, as we will see, which gives a natural path towards integration with silicon-based technology. Germanium as silicon has no nuclear spin, at least in its dominant, most common isotope, and it can be isotopically purified. So this means the lifetime of spins in germanium is also relatively long. The strong spin-orbit coupling means that by applying electric fields, we can cause fast operations of spin splitting between the states, and these states can be spin split even with weak magnetic fields, because the proportionality between the field and the energy splitting is much larger for holes than it is for electrons. And the small effective mass for holes in germanium means that the qubits can be larger, so we can think about qubits on the scale of 50 to even 100 nanometers, which is much easier to fabricate.